Light enters the eyes through the cornea, where it is then focused onto the retina. The retina contains millions of light-sensitive cells called photoreceptors, which are divided into two types, rods and cones. Scotopic vision refers to vision in dim lighting conditions, such as at night. In these low-light environments, the eyes primarily rely on rod cells, which are highly sensitive to light but do not detect color or fine detail. Scotopic vision is most sensitive to the color blue, but it has a very limited ability to distinguish colors overall. Rods function effectively at luminance levels below approximately 0.005 candelas per square meter. Photopic vision occurs under bright light conditions, such as daylight or artificial lighting. In these situations, the eyes rely on cone cells, which are responsible for color perception and visual acuity. Photopic vision provides excellent color discrimination. Cones function best at luminance levels above approximately 5.0 candelas per square meter. What we typically consider normal vision is actually a combination of scotopic and photopic vision. This overlapping region is known as the mesopic range, where both rods and cones contribute to visual perception. The S/P ratio is particularly important under scotopic conditions, where rod cells dominate visual perception. The S/P ratio is a multiplier that indicates how much of the emitted light is effective for human vision. These are referred to as visually effective lumens, VLs. A recommended S/P ratio falls between 1.8 and 2.0. Generally, white light sources have high S/P ratios, while yellow or orange light sources tend to have low S/P ratios. The blue hazard ranking measures the risk that a light source poses to eye safety, particularly in relation to exposure to blue wavelengths. Blue light is a type of high-energy visible, HEV, light, which refers to the blue portion of the visible light spectrum. Its potentially harmful effects are mainly concentrated in the 380 nanometers to 450 nanometers range. Blue light in the 450 nanometers to 500 nanometers range can offer certain benefits. In moderate amounts, blue light contributes to overall well-being and vitality. However, as with many things, too much can be harmful. Excessive blue light exposure can cause oxidative stress in retinal cells, leading to irreversible photochemical damage and worsening of cell injury in the macula. This is commonly referred to as the blue light hazard. The IEC 62471 standard defines the method for assessing the blue light risk from light sources and luminaires. Based on this standard, products can be classified into the following risk groups. RG0, no risk. RG1, low risk. RG2, moderate risk, requiring warning labels. RG3, high risk, even brief exposure to the light source can cause damage. Luminaires in this category are generally not permitted. EB refers to the irradiance of blue light emitted from a small light source, such as an LED. It is measured in watts per square meter, W/m superscript 2. Blue light irradiance, EB, is used to calculate the maximum exposure time and to determine classification into risk groups. This classification is proportional to the effective irradiance at the retina. The RG1 blue light irradiance limit is 1 W/m superscript 2, this is the threshold at which the transition from risk group 1, RG1, to risk group 2, RG2, occurs. KBV is a metric introduced in the IEC/TR 62778:2014 standard, application of IEC 62471 for the assessment of blue light hazard to light sources and luminaires. IEC 62778 provides clarification and guidance for assessing the blue light hazard of lighting products that primarily emit in the visible spectrum, 380 nanometers to 780 nanometers. KBV is calculated as EB divided by the illuminance, in lux. It essentially represents the ratio of blue light hazard potential per unit of luminous energy. These metrics help quantify the potential harm of blue light, particularly to the retina. EB and KBV are used by researchers to assess the photometric quantities of blue light that may pose a photobiological hazard. They form the basis for determining a product's risk group classification. In essence, EB and KBV are technical tools used to quantify and understand the hazards associated with blue light emissions, particularly from various light sources, thereby aiding in the implementation of appropriate safety measures to reduce potential risks.